Welcome to Astronomy Daily, your source for the latest news and discoveries from across the cosmos. I'm Anna.
And I'm Avery. We've got a fabulous show lined up today with some truly mind-bending science. We're talking about how our moon is slowly but surely drifting away from Earth, why alien civilizations might be much rarer than we thought, and how NASA guides spacecraft through the vast emptiness of space.
Plus, we'll catch you up on this week's busy launch schedule. So let's dive right in with something that might surprise you. Did you know that every single day the moon gets a tiny bit further away from us?
It's true. The moon is drifting away from Earth at about 1.5 inches per year. That might not sound like much, but over millions of years, it really adds up. And we can measure this incredibly precisely thanks to something left behind by the Apollo astronauts.
You're talking about those retroreflector mirrors, right? The Apollo crews placed these special mirror arrays on the lunar surface, and scientists have been bouncing laser beams off them ever since to measure the exact distance to the moon. It's one of the most precise measurements in all of astronomy.
Exactly. And the reason this is happening is actually pretty fascinating. It all comes down to tidal forces. The moon's gravity creates those familiar ocean tides on Earth. But here's the key. Earth's rotation is faster than the moon's orbital period. This creates a slight bulge in Earth's oceans that's actually ahead of the moon as it orbits.
So that tidal bulge is essentially pulling the moon forward in its orbit, which increases its orbital energy and makes it spiral outward. It's like a cosmic dance where Earth is gradually pushing its partner away. And there's another consequence. This process is also making Earth's days slightly longer over time.
The evidence for this is really cool. Scientists have studied fossilized clamshells that show growth patterns from 70 million years ago during the age of dinosaurs. Those patterns tell us that back then, a day was only about 23.5 hours long. The moon was closer, Earth spun faster. It was a different world.
And if we go way back to when the moon first formed 4.5 billion years ago, after that massive collision between Earth and a Mars-sized object, the moon would have been dramatically closer. We're talking about it appearing maybe 10 times larger in the sky. The tides would have been enormous, and days would have been just a few hours long. That early Earth-Moon system must have been absolutely spectacular to witness. Can you imagine those massive tides? We're talking about ocean tides, potentially hundreds of feet high, surging across the planet every few hours. The moon would have looked like this enormous disk dominating the sky.
And here's what's really fascinating about the physics. This process won't continue forever. Eventually, Earth and the moon will become tidally locked to each other, which means Earth's rotation will slow down until one day equals one lunar month, roughly 47 of our current days. At that point, the same side of Earth will always face the moon, just like the same side of the moon always faces us now.
That brings up something that really hits home for eclipse enthusiasts like us. The moon is gradually moving away, which means total solar eclipses are becoming rarer and will eventually disappear altogether. Right now, the moon is just the perfect size to block out the sun's disk during a total eclipse. But as it moves away and appears smaller in our sky, we'll start seeing more annular eclipses, where you get that beautiful ring of fire effect instead of totality.
The timeline is mind-boggling, though. We're talking about hundreds of millions of years before total solar eclipses become impossible. So while future generations will miss out on one of nature's most spectacular shows, humanity has plenty of time to catch these incredible events. In fact, we're living during a cosmically special time, the brief window when the moon and sun appear almost exactly the same size in our sky. It's incredible to think about how that ancient catastrophe shaped not just our planet, but continues to influence us today. Speaking of planetary formation and what makes world habitable, there's some new research that's pretty sobering about our prospects of finding alien civilizations.
Oh, this is the study about plate tectonics, right? The researchers are arguing that technological civilizations might need plate tectonics and something called the carbon-silicate cycle to survive long enough to actually develop advanced technology.
Exactly. The basic idea is that without plate tectonics constantly recycling carbon through volcanic activity and rock weathering, CO2 levels would just keep rising and rising. Eventually, you'd get a runaway greenhouse effect that would make the planet uninhabitable, kind of like what happened to Venus. The carbon-silicate cycle is really the planetary thermostat that keeps Earth habitable. Here's how it works. When it gets too hot, more water evaporates and creates more rain, which increases rock weathering. That weathering pulls CO2 out of the atmosphere and locks it into carbonate rocks. When it gets too cold, volcanic activity releases stored CO2 back into the atmosphere, warming things up again. It's this incredible self-regulating system that's kept Earth's temperature relatively stable for billions of years.
And Venus is the perfect cautionary tale here. Venus probably started out much more Earth-like, but without active plate tectonics to recycle carbon, CO2 just kept building up in the atmosphere. The result? Surface temperatures hot enough to melt lead, crushing atmospheric pressure and sulfuric acid clouds. It's a hellscape that shows us exactly what happens when a planet loses its carbon-silicate cycle.
This research has huge implications for SETI, the search for extraterrestrial intelligence. It suggests we might need to focus more on planets with clear signs of active geology, not just planets in the habitable zone. We'd want to look for atmospheric signatures that indicate active volcanism and weathering cycles. It's also related to what scientists call the Great Filter, the idea that there might be some extremely difficult step in the evolution from simple chemistry to a galaxy-spanning civilization.
The numbers are pretty staggering. The study estimates that it might take anywhere from 1,000 to 1,000,000 rocky planets for just one to develop into an Earth-like world with the kind of long-term climate stability needed for complex life to evolve and eventually develop technology.
And if this research is correct, it pushes the nearest potential extraterrestrial intelligence way out to maybe 33,000 light years away. Even more challenging, for alien civilizations to exist at the same time as us, they'd need to last an average of 280,000 years or more. That's a long time for any technological species to survive.
It really makes you appreciate how special Earth might be. We've got this perfect balance of plate tectonics, the right distance from the sun, a large, stabilizing moon, and probably dozens of other factors that had to line up just right. Of course, we're still looking, and that's where missions like the ones launching this week come in.
Let's talk launches. It's going to be a busy week. SpaceX has 4 missions on the schedule, including 3 Starlink launches to continue building out their satellite internet constellation, plus 1 mission called NROL-48 for the National Reconnaissance Office. That's the secretive one where we probably won't get many details about the payload.
The mission I'm most excited about is Blue Origin's new Shepard NS-35, finally launching Thursday after several delays. This one's carrying over 40 different experiments, including 24 student payloads from NASA's TechRise Student Challenge. Plus, they're taking thousands of postcards to space, which I think is just delightful. The new Shepard mission is particularly interesting from a scientific standpoint. Among those 40-plus experiments, they're testing everything from crystal growth in microgravity to plant biology studies. Several experiments are investigating how different materials behave in the brief microgravity environment, which is incredibly valuable for manufacturing research. The student payloads are testing things like seed germination, fluid dynamics, and even how social media algorithms might work in space environments.
The Starlink launches are pretty impressive from a technical standpoint, too. The constellation now has over 5,000 active satellites in orbit, making it by far the largest satellite constellation ever deployed. And SpaceX's booster reuse program continues to break records. Some of these Falcon 9 first stages have flown more than 15 times each. That's revolutionary when you consider that just a few years ago, rockets were completely expendable. The cost savings are allowing them to launch these massive constellation buildouts that would have been economically impossible before.
I love that. And there's something wonderfully old-fashioned about sending postcards to space in this digital age. And don't forget about Tuesday's Chinese launch, a Chang'e 2C rocket carrying what's described only as an unknown payload. The mystery always adds a bit of intrigue. Speaking of space missions, we've had a query from one of our listeners, Josh, asking how on earth do we maintain contact with all of our spacecraft in deep space? Good question, Josh. Once these spacecraft get beyond Earth orbit, they enter a realm where GPS doesn't work and navigation becomes incredibly complex. That's where NASA's Deep Space Network comes in. It's honestly one of the most impressive technological achievements that most people have never heard of.
The DSN is basically NASA's lifeline to everything we've sent beyond Earth orbit. It's a network that is made up of 3 massive antenna complexes, one in California, one in Spain, and one in Australia, spaced exactly 120 degrees apart around the globe. This means that as Earth rotates, at least one complex always has line-of-sight contact with any spacecraft in the solar system. The navigation challenges are absolutely staggering when you really think about them. Take Voyager 2, for example. It's currently at about 12.8 billion miles from Earth, in a completely unique position below the plane of the solar system. Commands sent to Voyager 2 take over 18 hours just to reach the spacecraft, and then another 18 hours for any response to come back. That means if something goes wrong, mission controllers have to wait more than a day and a half just to know if their fix worked.
The precision required for antenna pointing is just incredible. These dishes need to be aimed so accurately that they can target a spacecraft millions of miles away to within a fraction of a degree. It's like trying to hit a coin with a laser pointer from across an entire city. And they have to constantly adjust for the motion of both Earth and the spacecraft, plus account for things like atmospheric refraction and even the slight bending of radio waves by the sun's gravity.
This incredible precision is what enables those amazing gravity assist maneuvers that would be impossible otherwise. When Voyager 2 flew by Jupiter, Saturn, Uranus, and Neptune, each encounter had to be timed within minutes and positioned within hundreds of miles to get the trajectory exactly right for the next target. One small navigation error early in the mission, and Voyager 2 would have missed Uranus by millions of miles. The fact that we can execute these cosmic billiard shots across decades of flight time is testament to the incredible engineering of the Deep Space Network.
The precision is mind-boggling. These antennas can track spacecraft millions of miles away by measuring incredibly tiny time delays in radio signals and detecting minute Doppler shifts in frequency. They're essentially doing celestial GPS calculations, using the time it takes for signals to travel at the speed of light to determine exact positions and velocities.
And the range of missions it supports is incredible. We're talking about the Voyager probes, which are now in interstellar space over 15 billion miles away, Mars rovers like Perseverance and Curiosity, all the lunar missions, and everything in between. Each one requires constant communication for telemetry, commands, and navigation updates.
The future is getting even more exciting with optical communications. NASA's testing something called the Deep Space Optical Communications Experiment, or DSOC, on the Psyche mission. Instead of radio waves, they're using laser light to send data back to Earth. It's like upgrading from dial-up to fiber optic internet, but for spacecraft. If you'd like to find out more about the Deep Space Network, head over to our website at astronomydaily.io and check out our latest blog post, where we take a deep dive into the subject. I hope that answers your question, Josh.
Before we wrap up, let's quickly touch on a couple more stories. Firefly Aerospace got some good news. Their Alpha rocket has been cleared to fly again after April's failure. The investigation found that extreme heat and something called plume-induced flow separation caused the problem, but they've apparently worked out the fixes.
And mark your calendars for September 23rd. NASA's launching 3 space weather missions all at once: IMAP, the Carruthers Geocorona Observatory, and SWFO-L1. These will study how solar activity affects our solar system and help us better predict space weather that could impact satellites and astronauts.
That's particularly timely because the sun's activity has been ramping up significantly since 2008, after decades of relatively quiet behavior.
This has major implications for space weather and the safety of astronauts on future long-duration missions to the Moon and Mars.
That's all for today's Astronomy Daily. From our slowly departing moon to the search for alien civilizations, from busy launch schedules to the incredible engineering that keeps us connected to our robotic explorers across the solar system, there's never a dull moment in space science.
Thanks for joining us today. Keep looking up, and we'll see you tomorrow with more news from the final frontier. I'm Avery.
And I'm Anna. Until tomorrow, stay curious about the cosmos.